Okay, let's get started. So thanks for coming to the introductory day of the Magma Mondays workshop. This workshop is intended to help introduce folks to using Magma at a practical level. We're extremely lucky to have Daniel Tubbenhauer as well as John Taylor helping us out. They've agreed very generously to give a lot of their time and effort to helping us learn Magma. So we really thank them for that. Today we'll be listening mostly to Daniel, and in the coming Mondays we'll be listening to Don, as well as Daniel will be helping out. Just one couple of practical things. First of all, you're interested in tea or even just like cold water for drinking or something like that, you can go to Simri, which is on the other side of the quad. So during a break or you break beforehand.
Actually, during the graduation, there's a bar. There's a bar tent. That's right. So if you get bored, you should be able to get beer there. Yeah. Okay.
Not endorsing that, but it's an option. Yeah, if you don't know where Simri is, if you're not familiar with University of Sydney, just come after me, Daniel, Don, or here. They can help you with that. Also, I want to point out that today we're in this room, but all the subsequent meetings, which will be starting next Monday, will be in what's called the Oriental room, which is not along this corridor here. You go out the corridor, down and to the right. I'll try to put some signs up. Maybe give yourself 5 minutes when you arrive. It's always difficult to find rooms.
This one is in particular difficult if you don't know where it is.
Yeah. We're glad you made it, and let's get started. So today we'll have Daniel Tubbenhauer explaining to us the what, why, and how of Magma.
Yeah.
Oh, your camera's going and play off.
Yeah. Okay. Yeah. Let me just. Yeah, it's a cable problem. Sorry for that. Try to fix that till Monday. Okay. Thank you so much. Let me also thank the organizers, for Alex, who just gave the introductory speech, and Bregje, who is not here. Well, is here online and will be here on Monday. So if you have any questions, feel free to bother any of us, Alex, Don, Bregje, or me. And yeah, so what we are trying to do is, so I started Magma not actually long ago, and I really feel like I love it now. It has some difficulties. I will go to that today a little bit, but it also is absolutely fantastic. And in the end, what I really want is that you can just run one of my examples yourself, in the sense that you just program the code and just run it yourself. Obviously, you won't be on the level of someone like Don after 3 lectures, but you will be on my level, which is already something, I guess. And yeah, so plan for today, and plan for the rest of the week is that there are lecture notes on the homepage. So, and all the code is in the lecture. So the way you learn coding, or at least I learn coding, is I look at examples, I copy them and run them myself. And run them myself, and that's the whole idea. So while I will do that live for you later, like in 10 minutes or so, and while Don will give the talks, there will be code on the slides, and there will be code in that file that you can just grab and copy and run yourself. So we'll see that today. But first, I'm giving a little bit of a real slide talk, and then we go live. So if you have your laptop or device with you, give me 10 minutes, and then we are going to actually do some first steps in Magma. So we get you set up today, so you can run the first examples yourself today. And clearly, I'll come back to that in a second. Magma is large. It's just really, really large. It's mostly for topics in algebra, but essentially everything in algebra, you will find something Magma can do. And there's just no hope to cover that in 3 lectures. So we just pick out a few nice examples that Don has prepared, really, really cute examples in group theory, mostly, that we can run without any background. So I'm not assuming that you know very fancy mathematics, you just can run it mostly without background. And today I will go introducing a bit of background on the language, which I tend to like a lot. It's kind of written in a way you would write a paper. It's very intuitive. Yeah, so here are the lecture notes. So if you haven't downloaded them yet, please do. We will use them later, and I will keep them updated. So it's clearly not typo free. So if you find any typos, yeah, let me know, and I will fix them. So this example down here, we will do that in a second. So ignore it for now. So it's kind of things you can do with Magma fairly quickly. But the reason why I personally like Magma so much is that it kind of speaks my language. I'm kind of like combinatorics, I like algebra, and that's kind of the language Magma speaks. And whenever I have a problem, so down here is something we do in a second, like computing Galois groups. My first intuition is Magma should be able to do that because that's a problem in algebra. And I show you in a second how you would find that online, and you can just run it yourself very quickly in the online calculator. So, and it's really absolutely fantastic. There are thousands of pages of documentation, which is really helpful. We'll do that in a second as well. But it's really one of my main points, and people always get that wrong. So let me stress that. These are exact calculations, okay? So if you do a calculation with Magma, and you want to write a proof for your paper or your thesis or whatever, you can put it in your thesis because it's an exact calculation. In some sense, it's even better to do it in Magma than yourself. At least if you're someone like me, I wouldn't trust my own calculations. And I did that in like 10 papers or so. It just wasn't on only Magma, but several computer algebra systems. They always do exact calculations. They're not talking about numerical analysis. They will compute the Galois group kind of spot on for me. So I can just say, okay, I've computed the Galois group with Magma, let's put it in the paper, and that's it. And give maybe some code how people can do it, which is somewhat much better than just saying, oh, the result is the following, or the following calculation gives us, and then you do a 10-page calculation. So that's a really crucial point. And Magma is just extremely good at doing this. So Magma is one of the fastest systems I know for all of these problems. So usually the algorithms in Magma are really up to date. They're really fast. So what I did once when I started this, just was learning Magma and I wasn't aware what was really going on. So I was trying to count points on elliptic curves over finite fields. So I wrote a little program and I was very happy it was pointing counts, it was counting points on a finite field with 30,000 elements or something. I was really happy, it ran like in 1 minute. And then I found the internal Magma command for that, and it was like 0.2 seconds. So my own code was like a minute, and the internal Magma one was 0.2 seconds. Just to, well, okay, just to compare here. So usually the built-in functions are just ridiculously great. They're just really fun. And here's my list. So whenever you see something coming up in one of these, you should be able to find that Magma can do something. If you're interested in counting points on curves, that's maybe something like this one here. You can do it in Magma very efficiently. So Magma is one of the leading systems to count points on elliptic curves. If you wanted to do representation theory, you can do representation theory, whatever. You get the point. And what we are going to do is we are going to cover, well, I don't want to kind of assume that you know what counting points on elliptic curve really means. So we're going to go for the easier examples, mostly in the realm of group theory. And whenever, after the last lecture is done, we have a vote online on the web page, and you can choose your favorite topic here. Just vote for it. I would like to see more on, maybe you're completely into error correcting codes. I would like to see more on error correcting codes. We give a vote for it, and the one with the most votes will win. And we'll have some extra sessions later on, depending on the interest of people. And it's really fantastic. So if you want to give you an example, if you want to compute the Galois groups, don't do that by hand. You can just ask Magma to do it. It's super fast. We will also see that Magma has databases. So if you're interested in the monster group, for example, Magma knows that one, so you can extract data about the monster just without doing any calculation, just whatever, subgroup lattices or something like that. And it's really fantastic. So the algorithms are like ridiculously fast compared to what you can do by hand. It's just really good. So one point for me why I want to use Magma, well, this is a why, is because it's really good for what I like to do. And if you're like me and anything here is attractive to you, you might want to learn Magma. I should say here if it's not on this list, then it's probably not a good idea to use factoring. Okay. So if you really want to solve integrals numerically, there are better ways. Nothing is perfect, but this is kind of the list I have in mind. And if you really like one of them, let us know. We are happy to give an extra talk about it. Okay, wonderful. And we'll see that in a second. I'm almost done. It's almost my last slide. It's pretty straightforward. The syntax is really easy, and you can run it online, like live, like you do it now. So it's kind of, Magma is a little bit strange. It's non-commercial, so it's actually free, but they try to cover the on costs. So like keeping track of new algorithms, the documentation and all of that. So if you want to get it, you need a license. And I will show you in a second what to do, but you also have some license to give out if you want to. But the point is, in this course, you don't need anything to install. You can just run anything in the online calculator. And in my experience, usually that's enough for 95% of everything you want to do. So that's pretty cool. The highlight of Magma is you open your browser and you're ready to go. That's just absolutely fantastic. You open your browser, you're ready to go, and it's actually really quick. Oh yeah, here I say 90% is sufficient. Well, whatever, 1995. But it is really good. Okay, so we'll do that in a second. So my reasons for Magma are it covers the right range of topics in algebra and quantum mechanics in kind of a straightforward syntax, and it's essentially free to use, which is really, really good. So it's absolutely fast. You will see that momentarily. Good. So let's go to the how. So what I really want to do is I just show you how it works. So I pull up my browser and let's go to the website. So what I would do is I would just Google Magma. Magma has a bit of a tricky name, so you need to put something like USIT. Let me make this a bit bigger so it's pretty easier to read. I'll just Google it, and the first hit should be the website. They make it a bit bigger. Okay, and up here, you see the calculator. We'll go to that in a second. But you also see ordering, and you have the ordering instructions, what you need to do. It's pretty straightforward. You need to write them in email. And if your institution has access, you will send you a code and you can just install it. You don't need to do that. As I said, from 90%, it's fine to just click on the online calculator. And here it is. Right, fantastic. So let's zoom in a little bit. It's maybe a bit too much. Okay, so the whole idea is now the following. So let me go back to this file here, and everything we ever do in this course is in this file, and you can just grab it. So let me grab my example from Galois theory. I hope it's pretty straightforward. So the color, so the top is the code, and after result is the result you will see. And what you can just simply do is just grab it, copy it, and put it in the calculator. And I will explain in a second what this program does. And there you go, some result. Fine. You can do that with everything we are going to show you. And the kind of idea here is to do that while I'm doing it here and while Don is doing it during the other days. So let me highlight what is going on here. So all I'm doing is, essentially, it's pretty straightforward. So most of the code, you're just able to read it. Let me go into some details how to set it up. So I set up the integers, and the name for it is integers. And I set up the polynomial ring over the integers because I want to compute Galois groups of certain polynomials. And all I'm doing is I compute the Galois group, which is a pretty straightforward name, of this polynomial here, where I vary a and b. I let them run from -n to n for some specific n, and I collect the order of the group that I get. So here, down here, a is -5, b is -5. The order of the group is 120, which I could record the group itself, but the output of the order is a little bit clear. If you have a degree 5 polynomial, and you have 120 order Galois group, it will be the symmetric group. Okay, so here's a symmetric group. Here's the symmetric group again. Here's an order 10 group, and so on. And what you can then do is you can simply copy that. So the output, you take it. So Magma just did that, like the, what is it, 15, like the 120 different Galois groups in like a second. It's really, really efficient. And what you can do is you can just grab it and put it in your favorite illustration. So Magma is not really awesome for illustrating things, but you easily grab the output and put it in something else. And I just did that for my polynomial here. And this is one of my favorite examples of, I really use that in Magma, but I can't talk about this. So the point is, what kind of Galois groups show up if you take a random polynomial? And essentially everything will be a symmetric group. So here you see the output that I had just had before, just nicely colored, where A is on the x-axis, goes from minus 50 to 50, B is on the y-axis, goes from also minus 50 to 15, and I color-coded the size of the appearing groups. So the purple one, the dominant one, is a symmetric group, is a 120 order subgroup, that's fine. Yeah, so if you compute, so you just verify if you want, the kind of idea that almost all Galois groups, almost all algebraic integers, are actually really different. Right? I just varied it for two different polynomials and just put the Magma output in some like illustration. I really like this picture. I call it an ocean of symmetric groups. If I would, okay, what do you see on the axis? Well, on the axis, you would expect one of them is 0. You would expect some small cases, but ignore the axis, and otherwise it's essentially purple up to some funnily colored islands around. Yeah. So almost all Galois groups are difficult, and if you remember Galois' proof that you might have seen in Galois theory, is essentially to pick a random polynomial and show that its group is a symmetric. Which, there you go. It's very likely that you will be successful in it. And yeah, so this was like a thing I did in Magma, and you can see the code is like whatever, 10 lines, 11 lines. And it took me a minute. And at the end of the course, I would like you to just do the same. You have a problem, you want to give a talk, you want to get some output for your thesis or whatever. You write it in the code, get some output, and use it. Awesome. And there are many. Yes.
पक्का है ऑप्शन में लिख के रख लो हाँ
Can you mute them?
प्रोफेसर करना पड़ेगा बाद में पक्का है लिख के रख लो भाई
One of you is not muted. Can you please mute yourself? Okay, is the sound back again? Okay. Yeah, sorry for the interruption. But of course, if you have any questions, you can unmute yourself and ask your question. Just to be clear here. Okay, so this is the online calculator. And now, so there are many examples in this file. They're ordered by the various lectures. Let me just wrap up my little talk. Oops, the other way around. That's what we'll do. We just open the online calculator and we do some more fun calculations that you can just run yourself live now with me. And then, well, these are kind of the topics. They're all kind of in a way that you don't need to know too much math to understand what's going on. The Catalan number example is fantastic, that Don will do, and they will all run in the online calculator, and they're all in the file. You can all copy them and do it live. And they're all also exercises in the file that we will discuss after the lecture. So really the way to learn like any programming language is just copy old code and kind of arrange it to whatever you need it to be.
Excuse me, can I ask real quick, where is this Galois theory example in code?
Very good. That's an excellent question. Thank you so much. It is the first example in section 8.
8, okay.
Section 8A. I should have said that. Thank you so much. Okay, back to my slides. Okay, and eventually we'll have a vote on whether you're interested in whatever, Lie theory or representation theory or whatever, graphs. Yeah, so that's roughly the outline. Awesome. So let's go to the file. So we start now in section 4, which I call lecture 0, and hopefully it's pretty straightforward what's happening here. So you can always grab the result. Let me grab one of them. We can just copy it and put it in the online calculator. Paste. and it will run. And here's something funny that happens. So first of all, there's this funny symbol in front. Magma will ignore it. It's kind of the standard Magma symbol. You can ignore it. You can put it there by just copying, or you can put it out. It doesn't matter. You get the same result. Magma specific is a semicolon. So the semicolon is a way to tell Magma that you closed your sentence. We'll see that in a second. So one of the standard mistakes I always do all the time is miss a semicolon, and Magma will warn me if I do so. Let me just do 1 plus 5 here, 1 plus 4, and now it will complain that the semicolon is missing because it kind of doesn't know how to interpret the outputs. But if I just put a funny semicolon here, 1 plus 4, well, you get 2 or 5, 5. And you can see here that this is an exact calculation. If I put in 2 over 5, Magma will say, that's obviously 2 over 5. Hold on. So it treats it as a rational number. It won't give me some kind of an approximation. I can ask it to give me an approximation, but a priori it doesn't. You can do the same kind of operations, 2 to the 5. Maybe this one is a little bit more exciting. So 5 mod 2. Paste. Well, I hope that works out. So most of the commands are pretty straightforward. So addition, multiplication, subtraction, modular arithmetic, all pretty. I hope these examples are reasonably clear. Okay. You can also set up variables. So let's do that. So I set up a variable, and the way to do it is a definition symbol. Right? We define it. Go back to the online calculator. Okay, so I define it in the first line, and then I ask it what is x cubed, and hopefully that's 27, and then we tell me it's 27. So defining variables also works in kind of the straightforward way you would expect it to work. Here's my. Can you please unmute yourself? Okay, so and you can play around with that a bit more. Hopefully, the example is reasonably clear. So let me show you something different. So here you can also put more than one in a line. Let me grab it, put it in the online calculator. Paste. So I put more in one line, but it doesn't really matter because I told Magma to end it semicolon. So I define x to be 12, and then the next symbol is subtract 4. So hopefully we get down to 8. Yeah, so if you put one more than one in a line, you can. So subtract 4 here is divide by 4. So if I would do that again, so let's try that. Let's grab it and do it in the next line. Well, it treats the variable and it changes as we go along. So starts with 12, I subtract 4, I get 8, divide by 4, I get 2. So and I could now whatever subtract 1 or something, and I would get 1. I set it up and it changes the variable as we go along. Okay. Right. So we can do something like define 7 and multiply it by 7. Let's just do this, copy, and paste it into the online calculator. So it takes it, the last value it knows and multiplies it by 7. So 2 times 7, 14. It's pretty straightforward. It's kind of really absolutely amazing. Right? It's not so difficult.
Can I ask a question?
Absolutely.
So if you were just to do x is equal to x divided by 4, you would have an error message, right?
If I would just do, let me try to do it live. So x is just defined to x divided by 4. That's what you want. Good. Let's see what happens. There you go. You guessed right. It's an error. So that doesn't work. Because, you define something using something that is not defined in some sense, right?
Oh no, I meant if you had defined x before and you do this.
Oh. Okay, I see. So you want something like this? Oops.
Yes, thanks.
And that should give you the output. That's no problem.
Is it the same?
Okay, thanks.
That's correct. So the slash thing is exactly the same operation. Awesome. Okay, and there are plenty of other examples here in the file. But here's my favorite one. So let's grab this one again. Copy it. Grab it. Okay, we already had that. So if I ask Magma, what is 2 over 5? It will tell me, someone is not unmuted. It will tell me it's 2 over 5. Well, that's somehow very interesting. And let me tell you why, actually. So it says 2 over 5 is a rational number. So what Magma does is the following. So in the history of mathematics, there's a famous book written by Russell and Whitehead, Principia Mathematica, and they introduce the system of types. They want to avoid, maybe I should write it on the screen, that's probably a bad idea. They want to avoid this paradox that you could write x inside of x, which always leads to trouble. What they do is they assign types to different elements. And it turns out that it's not really useful for anything you really do in real world mathematics, but the computer scientists took it up. So a lot of computer algebra systems and computer system itself have types. They're not just data types. It's exactly the same idea. Everything gets its own type. And it thinks, well, 2 over 5 is a rational number. We'll see that in a second for Magma. And if I want to see it as a real number, I use this following trick. I just ask it to see it as a real number. I take it, put it here as a real number. And now it's a real number for Magma. I do kind of 2 over 5, some 0.4 and some precision of the number. Okay. So it has a data type. We'll see that in a second. Let's do that. So if you have something like 2, the way to figure out what the types are is to just write type. Okay? So x is 2. What is the type of x? Okay. So let's ask Magma what the type of x is. Ring integer element. So this function is just an element in the ring of integers. Well, makes some sense. Let's do another example. So it assigns a type to everything, and I will tell you in a second why that is important and why that is annoying in some sense. So if you do this one here, what is 2 over 5? Well, let's see. What is it? It's 2 over 5. Field rational element. It's a rational number. Yeah. Okay, so it's not an integer. But let's do something funny. Let's do 2 over 2. And let's output x for 2 over 2. Oh, that's 1. But Magma thinks it's a rational number. Right? It's not an integer for Magma because I defined it as a quotient. So Magma thinks it's a rational number. Interesting. So you always need to keep track. We'll see in a second why this is important. Right? I could do 4 over 2. It will tell me it's 2, but internally it thinks it's a rational number. Okay. That's very interesting. And that's really to avoid those errors, because it will not plan. Everything is in its own type. And if you want to run a function on integers, well, let's do this one. And then we'll run one. If you run a function on integers, but it's secretly what you get. It looks like 2, but it's actually a rational number. Then you can't run your function. And this is all to help you to field real elements. I put it in the real elements. This is all to help you to find errors in your code. So at the very beginning, this is super annoying. We'll see that in a second. You have something that looks like the object you want, but internally Magma thinks it's something different. So what you always need to do is to check the type, because certain functions will only run for that type. Magma does that to avoid errors. We'll see that momentarily. Okay, so let's do one more. So we could try something like this. Oh, let me just do this one. It's kind of the same that we did before, but let's just do it once more. Yeah. I multiply two rational numbers the result is an integer, but I multiply two rational numbers. For Magma, this is a rational number. Yeah? So always check the type. And why does that matter? Well, so you can try something like this. There's a function that is called isEven, which hopefully is self-explanatory. It checks whether something is even. And if I check whether 2 is even, it tells me true, and it already remembered. Let me just it remembered the old code I used. So let me just put this one in front. So it says 2 is even, but it says x times y, which outputs as 2. It says, oh, I don't know what to do. There's an error. Is even is not defined. Why? Because it thinks the x times 2 is a rational number, although it's not a rational. Well, it clearly is not, but it thinks it is. So it's not willing to run the isEven command because it doesn't make sense for rational numbers to ask whether they are even or odd. Magma is type-based. It is really the Principia Mathematica. It's type-based. Everything has its own type. Okay, so what one needs to do is the following. So let's try again. Here's another example. Copy it. Put it in the online calculator. Paste it. Okay, so let's see. 3 mod 2. That's 1. I hope you agree that 3 mod 2 is 1. I define x and y. Take x mod y. X divided by y. That is 3. It thinks it's a rational number, so it can't do the mod 2. But I could run this, right? The mod 2 just perfectly works for 3, but it doesn't work for the 3 defined by the rational number, because it's a rational number, so you can't do this. And this is, as I said, kind of really annoying in the beginning. And most of the mistakes you do in the beginning is some type mistake. We have something that looks like a matrix, but it's actually not a matrix. So be aware. So always ask, what is the type? And of course, there is a way around. Let's just do that as follows. Yeah, let me just pull up this one. So everything has a type, even something like a field. Okay. Bash. Z, ring of integers, Q, rational numbers, R, real field, C, complex field. I hope that makes some sense. What is the type of C? What is the type of Q? What is the type of R? What is the type of C? And even those guys have types. The ring of integers. That's its type. It's a field of rational numbers, the field of whatever, real numbers, and the field of complex numbers.
What else is one of the types? Like, is there anything else with the same type as C?
No.
But there's not like a ring type?
There's a ring. They live in. You could treat it as a ring. I'll tell you in a second what you need to do if you want to see it as well. I'm doing a different example, but the same example would work for this one. I have another one for you. And then we continue. Square root of -1 should be a complex number, and it is the field of complex numbers. And it immediately tells me that it is, well, complex number. Cool. Let's not. Literally everything has a type. Even the ring of integers has a type. That's the whole point of types, right? Everything has a type, and you can only play your games within one type. Integers. Ring of integers. And the type of 2 is an element of that, and the type of a ring of integers is a category. Okay? That's what it's called. The type of integer ring is a category. So everything has its own place in Magma. So you always need to be aware where you are and what Magma thinks you're doing. Right? Remember the example that I had the number 2, but I couldn't ask it, is it even, because it's actually not a rational number for Magma. Okay.
The ring of integer element.
Yes.
That's
Fine. That's just what it is. Yes. The ring of integer elements is a category. Yes. You won't use that so much in practice. But yeah, that's what it is. I'm sorry.
number 2. Or no.
That's the whole ring is a category.
The whole ring is a category.
Whole ring is a category.
Yes,
And then there are elements of the ring which are a different type to
that's right.
the ring again. So the integers round brackets has its own type, and an element of that ring was it well, it's a separate type. And there's a hierarchy of types as well. And category runs with top.
Right. So let me, where are my friends here? So you can do the following. Well, is 2 in Z? It is. Is whatever in Q? It is. Is it in Z? It actually is. Kind of fun. The types are really straight. But is this one in Z? And no, it isn't. And I hope that makes some sense. Okay.
So even though it's not the right.
Yes. And I will tell you the second why it's the wrong type, but it lives in Z. So it already knows that it's there. You just need to tell it. I will tell you now. You just need to tell it actually it is an integer. So let me just do this. So I have a few more examples here. Here you go. Okay. So what you need to do with my example, just to answer your question, is you need to use the following. So it already knows that it lives in the ring of integers. There should be a way to tell it it's an integer. And it's called cast it. I cast it into the integers. And what you need to do is you need to put the one in front and put the exclamation mark. And then you can do the mod 2. So let me just do it this way, maybe. I just wrap my number here. Right, so now it's an integer. So I can do in mod 2 and it should be 1. But if I just do it itself, it's a rational number. And it gives me an error, by the way. Hey, I'm a rational number. I can't take mod 2. And this is kind of a very important operation in Magma. It's called casting. So you have a matrix, it looks like a matrix. Magma knows it is a matrix, but it still treats it as a whatever. Then you need to, and you want to use matrix operations, then you need to cast it into a matrix. And this type of mistake happens all the time in the beginning. It's very annoying. That's why I'm mentioning it. But eventually it helps you to prevent errors. Just think of you have a large code, and Magma will just go along with it. But eventually there's an operation you don't want really to do on the type of number you do. Just Magma goes along, and then the error travels along. And then you would need to find the error in a very long code, which is kind of really painful. But Magma immediately tells you, by the way, you shouldn't do this, and you can immediately kind of fix it. So this will happen all the time. So I'm warning you. Just you will get used to it. It's just if you're used to some other computer algebra systems do it differently. So Mathematica, for example, is very agnostic. It just whatever you do, it just does something. But the problem then is it does something, could be the wrong thing to do, and it won't tell you that it was wrong. So here we have this kind of type system, and it's really important in terms of Magma. It will always stop you immediately from doing what you want. So maybe one more example, and then I should move on. So Don will come back to types, I think, as well. Let's do this. 6, 2. What is the type of 6 over 2? It looks like 3. It's I forgot to define Z. Yes, very good. So good. So the type of one of them is a rational number, and the type of the other one is an integer because I casted it.
Can I ask you real quick, how to
Absolutely.
check if, let's say, x over y equals 3? How do you write it in Magma? The question, x over y equals 3, it should be true or false, right? So
Let's
how
try.
can-
Very good question. Let's see.
Is it true or it's not true?
Well, it tells you 3 equals 3.
EQ.
But what you need to do is the following. So you ask it, is x over y equal to 3, which is EQ? And then it will tell you it's true.
Great, thank you.
Any other questions?
Could you use for integers and integer ring? Are those the same command? Are those two different commands for the same thing?
Use integer array?
Yeah.
Yeah, it's the same. I only wanted to use integers actually. Okay. Right. Cool. Awesome. So, types are always like annoying, and we'll see, or nice, depends a little bit on what on your point of view. So let me set up more standard notation. So maybe you want to set up set in Magma, and the notation is kind of what you would expect. You use curly brackets. Let me do this one, maybe. Let's see what this is. And it's pretty, there's our EQ again, which is really just the equal command in Magma. Let's do it. It's pretty straightforward. I set up x as a set 1, 2, 3. I set up y as a set 1, 2, 3, 3. You might say now, wait, it doesn't make sense, or it's set should be the same. So I ask it, is x equal to y? And it's true. So in a set, you can never have repeated entries. It's a set, right? You can still write them. Magma will just kind of ignore them. Z is 2, 3, 4. Is x equal to z? Well, it's not. You can now do the usual things here would be join, meet, difference, and symmetric difference. And they do exactly what you think they do. Join is just join. So x join z is what you see, right? Because you again delete duplicates. Meet, difference, symmetric difference. Is 1 an element of x? Is whatever an element of x? It's not, whatever, 5. This was supposed to be a 5. It's not. So, pretty straightforward, as you would write it in a paper, I guess. It's again very important to keep in mind these are now sets, right? So if you write something like 1, 2, 3, 3, it's just 1, 2, 3.
And how do you write not equal?
Sorry?
How do you write not equal? The negation of equal. What was not equal?
Just any.
NE, right? Not equal. NE.
Thanks.
Yeah, so number of elements. Let me get rid of some of those here. Has 3 elements. Number of elements of y still has 3 elements. It's really a set.
But if you put like 1, 2, 3, 3 over 3, how many elements?
You want to put 1, 2, 3, very good question, 3 over 3, and you want to know the number of elements of x, and it's still 3. That's very interesting, yeah.
If you do 3.00 divided by 3 instead.
No, let's try. No, come on, let's try. Still 3. So it knows actually that this is an integer. It just treats it not. It just treats it not as an integer, but in this case it does. Specific things.
Maybe this point where Magma uses in some cases automatic coercion.
Right. Right. So what Don just said, maybe that was a bit difficult to hear online, is in this case it automatically casts things, which is element is a subset.
Can you repeat the question?
I didn't understand the question. What is the question? Oh, not that I know of, Don.
So what's the question?
Whether there's an identification of the set one with one element.
Yeah.
And the number one.
No.
I don't think so.
Just one point about
Yeah.
that. I think what happens is that when you define a set, Magma will know a universe for that set, which in this case, when it sees number one, it sees an integer. And so the universe is going to be integers. And then it's possible it will coerce things into that universe. So actually, I've never tried this. What would happen if you put the 3.0 over 3 at the beginning?
Aha. So what Don is guessing right now that the first entry kind of defines its universe. We'll see. Nope.
No? Okay.
Oh yeah, but we don't know what's going on here.
But I just tried, like, if you print the output, it converts all of them to real numbers.
Oh, they're all real numbers.
Okay.
Okay.
So it takes like the highest.
Okay.
Yeah. I think that's right.
Well, you said it doesn't make sense because they're just worth multiple numbers, but then they will.
Oh, yeah. Okay.
Right.
Just have a look at it itself then. That's
Right. So the guess is now maybe right that it takes kind of the highest class, in this case a real
Yeah,
number.
so if you print out the specs.
Oh, should be capital X. Small p. That's it. That's what it is. Print. Oh yeah. So they're all just real numbers. Thank you
If
so
it
much.
went the other way, would it just be integers? Do you think?
When I put this one, no, I don't think so. Let's try.
Or that- There we go.
So it really just takes the highest class.
okay. Yeah, so universe, yeah.
Interesting. There you go.
But you could coerce this to being integer by doing the same thing. We or integers. Exclamation point.
Let's try. Well, I would need to define. You want to do this?
Or no, I meant on all of it.
Oh, let's try this one first.
Okay.
Well, that definitely makes sense. And now you want to do something like no, because it's a set, you can't class the set into the integers. But I can do it on every
Oh,
element.
you gotta be making, guessing all of X.
Right. It's a set, right? It's not an integer. So you can't class it into the integers.
Doesn't do anything. 0.5.
Right.
There's a command called change universe.
Very good. So let me maybe pull up this one. So you can use the standard notation to create sets. So y is 1 to 9 by 2. This just means I take every second entry, yeah? And z is x squared for x in 1 to 10. So let's print out, is 4 in z? No, it's not, because I started 1. I can print out y for you. I started 1. Okay, fine. I started 1. I can do the following. Okay. 1, 3, 5, 7, 9, I guess. Yeah, it's a set 1, 3, but whatever, 7, 9. Just 1 to 9 by 2. Step 2. And the bottom set is the square integers up to 10. So hopefully makes some sense. So you can just put the usual set notation using the semicolon, and then you get the and put the condition as well.
And do that and ask if it gives me the 1 to 9. Why isn't it just coming out?
That's a good question.
Because because sometimes you want very large things that you don't want to actually have to create them to
Right.
use them.
So sometimes Magma avoids showing you the output and let's force it to show you the output. Because usually if I use I could have just used 1, 3, 7, 7, 5, 9, right? But usually what I do is 1 up to 1,000,000, and you don't want to put that stuff. So let's do this one. I set 4, 2, 16, minus 3, 0. Maximum of A, minimum of A, my favorite, random of A. So let's do it. Well, maximum I hope makes sense. Minimum I hope makes some sense. And let's try again. Random creates a random element. Yep, picks up a random element. Sometimes it's very annoying, we don't see it today, but sometimes the algorithms in Magma are randomized. So they give exact calculations, but it can happen that you have an algorithm that actually runs what you call a simulation and will get an exact calculation in the end. And then you will see something like this happen. So the output will change because the input has changed.
I'm not sure if we're just about to say this. Is there a way to set a random seed in Magma?
Right. Yes, but yeah. Yes, go ahead, Joe.
I mean, it's sort of saying analysis. So you can like cleverly define set as one. But if you actually want to list those out, very easy to get this by saying the set of x colon x in 1 dot 200, and then when you print that, it will have all of the elements. So it's like taking the clearly defined set and forcing it into a.
Yeah, so you can always force it to tell you that. Whether that's smart with a set of size 1,000,000 is another question. So I'm running a little bit late, bad on time, which is fantastic because you're asking so much questions. That's how it should work. So let me just tell you about multisets. We just need to set up the notation. So if you want something that contains an element twice, you use the brackets. And essentially everything. So this is now a multiset. So don't mix sets and multisets. Magma will be unhappy. But you can cast one into the other. I'll show you in a second. And this one has now repeated entries, right? It says 1 appears twice, and I have a 2, and I have a 3. And essentially the same operations work on multisets. Let me just pull up this one. All right, so one is a set. That's this universe, and the other one is a multiset. So you somehow can't put them together. And maybe I actually do have an example in the file, but you can essentially do the same, right? So essentially the same things we'll go through. Depends a bit what you want to do. Looks exactly the same. The multiplicity is doing what you think it does. Counts a multiplicity of 4 and it appears twice, right? Why does 4 appear twice here? Because minus 2 squared is 4. So we can define a multiset and run the same operations. And you can do the join, whatever. But let me just finish by showing you the type you should actually use, in my opinion. Let's say list. List is this one here. We'll do it with square brackets. Batch. Okay. The first one is the list from 1 to 10. Again, 2 dots means I go from 1 to 10. And the second is the list 3, 6, 6, 2. And the difference between a list and a multiset is that a list has entry. In a set, I don't have any order. Okay? A list is like a sequence. You have first entry, second entry, third entry. So I can ask it what is the second entry of y, for example. And the second entry of y should be 6. Someone please unmute yourself. Okay. number of elements is 10. And it again uses this output that we discussed, like shorthand output. And this kind of, so lists are really important because now you can ask, what is the second element? So let me just show you something. Let me put it into a set. Oh, did I get the set right? Oh. Put it into a set. And ask, what is the second entry of that set? The question doesn't make any sense. The set doesn't have any order. And it will complain. And the set, this operation doesn't make any sense here. So list is really your list state. You have access to the various entries. And they have the same type of operations. For example, let's do this one. Running over time, but we started 5 minutes late, so I'm going 5 minutes over time.
What time are you planning?
I wanted to stop it after 1 hour, like that.
I think you said it was 5. So
Yeah, no, the room is fine. If someone wants to stay, we can go on, of course. Okay, so I can do the following: 1, 6, 4, 3, 9. And I define this third entry of x to be 5. Now the third entry of x is 5. So lists are really good. You can do the following. You can append, and well, let's just do it this way. Append an element to x. And this now makes sense. For a set, it wouldn't work. Yeah, append, put it on the end. And as you might have guessed already, there's of course also the prepend, which let's do this one here. Remove the entry number 3 from your list. It removes the number 5, number 3. And you have all these operations on lists. So usually I would recommend to work with lists, and you can cast them one into the other. So that's what we will do now. So they insert and reverse, do exactly what you think they do. Sort is interesting. So maybe let's run sort. It will do something that you can't do on a set. You can't sort a set. Doesn't make sense. I should output x. 1, 3, 5, 6, 8, 9 looks good to me. Just does exactly what you do, and you can do that on. Yes. That wouldn't work if I would put something that would complain. I can't run by command. But usually you would expect. You could put something more fancy in the list, obviously, but you would expect that this will be a number or something.
So if I may, removes the whatever stands at position 3, right? Not the element 3.
Correct. Remove whatever. Let's do it again. Remove whatever is at position 3. So the element 4, the element 3 is at position 4, and the element 4 is at position 3. Sorry, I output it twice. That makes sense. The element 4 is at position 3. It removes the element 4. If I want to remove the element 3, I need to do it this way because it's a forced element.
But x itself still remains unchanged, right?
If I do this, x itself remains unchanged. That's what I did before. There you go. X itself is unchanged. If I want to change x, I need to do this. Oops. I need to do this. And now x is 1, 6, 4, 9. So if I just do remove, as you just said, without doing anything, it just gives me the output of that operation without changing the variable itself. Okay, some more examples. And this one is maybe interesting. So let's do first define A, and it's a list. That's what you always do. You need to cast it eventually. So I have my list 2, 5, 3, 3. 2, 5, 3, 3. Perfect. And maybe I eventually want it to be a set. And then you just say, well, take the sequence and put it into the set. Let's see what happens. So B is sequence to set A. Okay? And we can now output both of them. So A and B will be outputted. So what is set to sequence doing? First of all, it removes any order you gave it because entry doesn't make sense for a set, and also removes the double appearance for it. So it doesn't make sense for a set. But you can kind of cast it into a set. Okay. You can do the inverse operation. So sequence to set is exactly doing what you think it is, and set to sequence is exactly doing what you think it is doing. So let's do it. Set to sequence B, our final output, and you have lost the entry, right? A list, a sequence is kind of a final structure. Now you only remember the entries, and they will appear exactly in the order position. Yeah. So I lost the order and I lost the appearance of 3, but you can still go from one to the other. And it actually does it nicely, right? It doesn't complain, oh, my first element doesn't, my first thing doesn't look like a set, because it has 3, 3. It just somehow does it automatically. It just removes those entries. Here are our conditionals. So, and you can cast the list into a multi-set or multi-set into a set. All these, and I have done them all in the file for you. Okay. Maybe I'll finish with this one, and so let's just do it because it's kind of important. So equal is equal, not equal is NE, greater equal is GE, lower equal is LE, greater is GT, lower is LT, in is in, and we have AND, OR, and NOR. So let's try one of them. For example, this one. Or maybe this one is fun. Okay. And you can essentially ask that for everything. We'll just check whether they're equal. So are they equal? And no, they're not. And I can't really do anything because one of them is a. How should I compare them? One of them is a sequence, a list, and the other one is a set.
It tries to auto force one into the other probably. Like,
say it again.
Does it try and force the converse one into the other one type into their type and make them comparable? Or they can do if you compare like a real number and an integer.
Right. For some structures it does. For some structures it doesn't, because I could just do here. What is it? Set to sequence. And so it knows that it's actually epsilon. So what's happening here is the following. We can do that, fine. The problem is, and we can do what the point is, we have an integer, which treats like a type of a regular number, it still knows it lives in the ring of integers. But in this case, I mean, set is a very different object than a list. So it just doesn't know what to do. It says, nope, no way. And it doesn't really make sense because my set to sequence and sequence to set will lose information, while just a straightforward, I want it to be an integer doesn't. Yeah, so let's try another one. Hopefully this one is pretty straightforward as well. So x is 5, is x equal to 5, or x equal to 4, and x equal to 2. So now I let you make the mental yoga what the result is supposed to be. It's not so difficult. It's true. But I can, yes, exactly.
No,
It's in order. I could try the following.
Just and first and then or.
Well, they're doing the precedence order. I can't remember.
Right, I can't remember either.
Be sure.
Right, we could parentheses. I think the or comes before the end, but
Oh,
So put the parentheses, yeah, after the 4, not after the 2.
oh yes. Bash. Well, it's still wrong because it's
Oh, yes, that's pretty clear.
let's do it like this, then we can check. Yeah, whatever. Yeah, so usually I would recommend to put parentheses to not get confused, and I didn't do it. So I get confused. That's what happens. All right, let's try the following. Again with conditionals. Where's my slot? A is 3, B is 5, B is 4, C is 5. And I can ask it to do something with an if operation. If I'll turn it up later. So if A is greater than B, then C is defined to be A times B. So what is C now? Let me give a second to think about the mental yoga. So it's either 12 or 5. You just need to decide whether A is greater or B. It's still 5. So if A would be greater than B, it is not. But then you would do this. So let me just change the order form, for example. So B is greater than A, so now it's 12. Hope that makes sense. You can ask if conditions. And there are plenty of examples of if conditions in the file itself. Let's try another one. It's just written differently. So from now on, I usually like to write it a little bit like this. The same code, but I put it in more lines to make it like kind of easier to read. So I find them, have my little if going on here. So if is kind of this closed environment, that if then, and if, and then it's kind of the same, right? This is really the same, it's just arranged differently. Well, we can do the following. If else, let's try it. It starts off as the same. Else, C is defined as 6. So if the condition is not true, we define C as 6. So let's see what happens. Yeah, 6 now. And if I change them again, then it won't run into the else. I hope that's reasonably clear what's going on. If then else. Here's a little bit more funny. So let's see if we understand this one. Okay, x is 5. That's pretty good. If x mod 4 is 0, then, well, print whatever. If x mod else if x mod 4 is 1, then print, yeah. Else if, and you can put as many else's if you want, x mod 4 is 2, print, and you can end in else, which is the case x mod 4, 3, and print whatever it is. So now I let you do the mental yoga. What should be the result here? I hope that makes some sense. And if you change it to your favorite larger number, maybe I put 3. Oh, okay, maybe I put 1. There you go. That's it. To just list conditions. If L, and you can do L if is a command, and you can do as many as you want. And I could put an end here, whatever, and whatever, x equal to 8. And let's do a number that is now divisible by 4. Let's see what happens. It's still the old output. That's what's happening here because it doesn't have any output.
No, it's just because it doesn't satisfy anything. So that the last thing, the else
Oh.
is not a conditional.
Yes. Oh, yeah. Okay. It doesn't satisfy anything, it just does the else. Exactly. Yes.
The last time it was else if then.
Yeah. Okay. Yes. Very good. Right. Let's put it over here, and then it will change again. Hey, hooray! I understand how and and or work. That's very good. That's a good start. That's an excellent start. Other things we can do. Let's try case. Case essentially checks the case sign is sign. So let me just maybe sign of x. I'll put it as well. Sign of x is 1, right? Positive number, and case just checks. Case, what is sign? When it's 1, output x is positive. When it's 0, output x is 0. And when it's -1, output x is negative. So we do, for example, -1. It's negative, or let's see. Again, so let's do one more. This is select. So here was this very complicated thing. You can do the following. So select variable condition select value if true, value if false. So let's see what's happening. These are all conditionals that you can play around. So 1 greater than 0, select 1 else -1, and output give me s. So it should be 1, right? So select if true and select the other one if not true. Let me try to find something that is not true. Something like this, and it will select. Exactly. I have one more, but you're free to run away. I can also want to tell you about loops. Then we are fine. So you're free to go. It's not necessary to stay. I won't check. I also won't check here. You're free to leave. Let's do it. And this is one of my favorites. Bash for I in do. Okay. And then give it a command. I squared. So hopefully what we will see is 1. Well, let me just do it. I can't. So if you get too used to do this, you can't go 5 minutes to your head anymore. So be aware. 1, 4, 9, 16, and 25. Hopefully makes some sense, right? So it's the same syntax as for if, just for whatever do the forward.
So if we have this in the program, where does I squared gets assigned to?
Here right now I just printed. It's assigned to nothing.
Right. And in the program, will it also be printed, or?
I don't understand the question. In the program, will it be printed? Oh, so
like you write a code, right? And you have this fragment. Will you see it printed, or it just will be not seen at all? Without explicit print command.
I'm not using a print command at all, and it's printed. I'm not right now. It just outputs I squared 4 or 5 times.
The expression by itself presumes print. Just an expression.
Expression by itself is printed automatically. Let me try again. So here's a little bit easier example. Here's an expression by itself, and it will just print it. Is that okay? I take that as a yes. If you want to define it as something, you need to do something as following type. I set some output, whatever it is, I will fill it in anyway. And for I in 1 to 10, I append that funny number mod 7 to my set. And that's a calculation you don't want to do in your head, but Magma has no problems of doing that. So maybe I can do the first one. 1 cubed plus 1 plus 12 is 14. Guess 14 mod 7 is 0. So that's the first entry you see. Don't let me do the other ones that probably fail anyway. Okay. But if you want some, you can change in the 4, you can change a variable. That's what I'm doing. I have a variable out, and I change it in the 4. And in every step in the 4, I just append a certain element. I could do something easier. I could just append I guess, but maybe that's too boring. So let me append I squared. 149. So, but before, there was just an expression and it was just printed, and now I have a variable and I change it in every step. And then I output the variable at the end. Hope that makes some sense. Well, we could do the following. So the 4 one is fantastic. And sometimes there's something a little bit better with while. So you will end up probably most of the time using 4 as a kind of thing that changes. But there's also while, and it does exactly what you think it does. So let's have a look at an example. While a certain condition is true, do something. And usually I don't recommend to use while. I'll say the second while. Okay. N is whatever number it is. While n mod 5 is not equal to 0, add 1 to n. Okay, so it should stop after a few steps and should give me 455, right? Just checks in every step. I could do something like maybe a little bit bigger, 15. So it will go all the way up to the first number that is divisible by 15. Okay, so you can do a while. Whatever is in the middle here, it will be repeated while the condition is true. And that's dangerous because you might end up in a loop where the condition is just true all the time. So let me give you an example of that. So usually do 4, because 4 is 4 steps from A to B, do the following. So it always stops. A while condition is true, do something. Condition could be true all the time. And that's, for example, let me just create a loop here. 55, 15, and let's add 0 in every step. And yeah, let's see what happens. Oh, while is, give me a second. Do I get it right? Oh yes, very good. Thanks. So while it is equal to 0, do at nothing. So it is equal to 0 in the first step, it is equal to 0 in the second step, it is equal to 0 in the 100th step. Maybe I should not write that. Okay. There is a calculations are restricted to 120 seconds. So in case you want to check out the power of the online calculator. So let's cancel the calculation. So this will run forever. So that's the danger while. In this case, it's quite clear, but imagine you have a really long code and you have some more sophisticated while staying somewhere. And for some options, it might run forever. So while is always a bit dangerous, but you have the option to use while. And the last function I have for you is repeat. And then we are done for today. So 4 is kind of my favorite. And this one is fun. This one is might not terminate, but the probability is like it doesn't terminate. So what do? I take the set 1 to 1,000 and I repeat a certain operation until something is true. Okay? I repeat until something is true. I repeat setting A to be a random element from my set. And I repeat until, well, my number is prime, right? Is prime is just checking whether it's prime. And then I output A. Well, this has probability 0 to not terminate. In principle, the random algorithm could, in each step, select the same element or something. So here, and this is a random, so I should get a different result every time.
You can actually leave out the equal true.
Sorry?
You can dig out EQ true.
What Don just said is you can actually do the following. So let me just put in the shortened version, which I find less clear, but you can do the following. Okay? It's exactly the same until whatever is prime, and it will do exactly the same. Again, very dangerous if I hit a set where I have no prime, like this set. 120 seconds of calculation. But I'm done for today. So thank you so much for coming.